There are an estimated several thousand star systems within just 50 light-years of Earth. That's our cosmic neighborhood close enough, in astronomical terms, that we should know it better than almost anything else in the universe. Here's the unsettling truth. We haven't directly seen most of them. Not photographed, not resolved, not confirmed with certainty. Many of our literal next-door neighbors, stars close enough that their light left them before you finished reading this sentence, remain either completely undiscovered or catalogued only as faint statistical hints buried in decades of data. And it gets stranger. In 2013, not in some distant, primitive era of astronomy, but well within living memory, decades after we'd already landed on the moon, astronomers discovered an entire star system sitting just 6.5 light-years away, close enough to be the third nearest star system to our own sun. It had been there the whole time. We simply hadn't noticed. If we can miss something that close, for that long, the question becomes genuinely disturbing. What else, sitting even nearer, are we still missing right now? Let's start with why this is even possible, because it cuts against almost everyone's basic assumption about how astronomy works. Most people imagine that nearby automatically means easy to find. That's true for bright stars like Sirius or Alpha Centauri, visible to the naked eye, catalogued since antiquity. But brightness and distance are not the same thing, and the gap between them is exactly where this mystery lives. A star's apparent brightness, as seen from Earth, depends on two completely separate factors: how much light it actually produces, and how far away it is. A blazing, massive star could sit far away and still look bright. A small, dim star could sit relatively close and still look almost invisible. And the overwhelming majority of stars in our galaxy, roughly 70% or more, belong to exactly that second, unglamorous category. They're called red dwarfs. Small, cool, faint stars that produce a tiny fraction of the light our own sun does. The star system discovered in 2013, called Y0855, wasn't even a proper star. It was something dimmer still, a brown dwarf, sometimes described as a failed star, too small to sustain the nuclear fusion that powers true stellar objects. It emits almost no visible light at all, glowing instead faintly in infrared, the wavelength associated with heat rather than light. To the naked eye, and to essentially every telescope built before infrared astronomy matured, it was functionally invisible, despite being one of the closest objects to our entire solar system. Here's the detail that should genuinely surprise you. Y0855 is colder than most planets. Its estimated temperature sits somewhere in the range of -48 to -13 degrees Fahrenheit, cold enough that some scientists have speculated it could host frozen clouds of water ice in its atmosphere, an almost unheard of feature for anything resembling a star. It wasn't hiding behind some other object. It wasn't obscured by dust. It was simply too cold, too dim, too quiet for centuries of astronomers using visible light telescopes to have any chance of noticing it at all. And this is where the deeper, more disturbing pattern starts to reveal itself. Our entire multi-century history of cataloging nearby stars has been fundamentally biased toward the loud, the bright, and the hot. Anything faint, cold, or dim, even sitting practically on our cosmic doorstep, has had a real chance of slipping through, undetected, for as long as our tools remained limited to visible light. Let's talk about exactly how astronomers eventually catch objects like this, because the method itself reveals just how much of our nearby universe still exists in a kind of observational blind spot. WISE 0855 was discovered using data from the Wide Field Infrared Survey Explorer, a NASA space telescope launched in 2009 specifically to scan the entire sky in infrared wavelengths, the part of the spectrum associated with heat rather than visible light. Infrared astronomy matters enormously for exactly this kind of search, because even objects too cold and dim to produce meaningful visible light still radiate faint heat, which infrared instruments are specifically built to detect. Before infrared sky surveys matured, in roughly the last few decades, our entire picture of nearby space was built almost exclusively using visible light, the same basic method humans have used since the invention of the telescope. And visible light, it turns out, is a surprisingly poor tool for finding an entire category of objects that don't reliably produce very much of it. Since WISE began its survey, astronomers have used its data to identify dozens of previously unknown brown dwarfs within just a few dozen light-years of Earth objects that had been sitting there the entire time modern astronomy existed, simply outside the range of what our primary detection method could actually notice. And brown dwarfs are just the beginning of this problem. There's an entire category of objects even harder to detect and even more unsettling to think about: rogue planets. A rogue planet is exactly what it sounds like: a planetary mass object that isn't gravitationally bound to any star at all, drifting alone through interstellar space, either ejected from a forming solar system through gravitational chaos, or, in some theoretical models, having formed independently in the first place, condensing directly from a collapsing cloud of gas the same way a star does, but without ever accumulating enough mass to ignite nuclear fusion. These objects produce no starlight of their own to reflect, because they have no host star to reflect it from. They don't undergo fusion, so they don't generate significant heat the way even a cold star does. They are, in the most literal sense, some of the darkest, most detection-resistant objects that could plausibly exist in interstellar space. Current astrophysical models suggest rogue planets could be genuinely common. Some estimates propose there could be more rogue planets in our galaxy than there are stars. Let that sit for a second. Not a smaller, minor category tucked in beside the stars we already know, potentially more numerous than the stars themselves, drifting silently through the vast spaces between star systems, essentially undetectable using any conventional method of astronomical observation. How do we know they exist at all if they're this hard to find directly? The same way we've confirmed almost every other invisible or near-invisible phenomenon in modern astronomy, through indirect evidence. Gravitational microlensing surveys, the same basic technique used to hunt for isolated black holes, have caught brief, unmistakable signatures consistent with rogue, starless planets drifting past background stars, their gravity subtly bending and magnifying that distant starlight for a matter of hours or days before the alignment passes and the signal disappears forever. Each one of those detections represents a single, fleeting glimpse of an object we will, in most cases, never be able to directly observe again. We don't get to follow up. We don't get to point a telescope back at where it was and confirm it's still there. The alignment that revealed it existed in the first place is gone, permanently, the moment it ends. Which means our confirmed catalog of rogue planets represents an almost unimaginably small fraction of however many are actually out there, quietly drifting through the dark spaces of our own galactic neighborhood, potentially passing closer to our solar system than we'd be comfortable knowing about, with absolutely no way for us to track them, warn about them, or even confirm their presence, unless we happen to be watching exactly the right patch of sky at exactly the right moment. Let's bring this back to something a little more grounded, though, because it's not just exotic brown dwarfs and starless rogue planets we've been slow to find. Even ordinary, genuine stars, small, dim, but perfectly normal red dwarfs, have a surprisingly recent history of discovery within what should be our best-known cosmic neighborhood. Proxima Centauri, our single nearest star beyond the Sun, sitting just 4.24 light-years away, wasn't discovered until 1915 by astronomer Robert Innes. Using careful photographic comparison techniques, despite the fact that its slightly more distant, much brighter neighboring stars, Alpha Centauri A and B, had already been known and studied for centuries. Proxima sat there, closer to us than any other star in the universe, invisible to the naked eye and unnoticed by generations of astronomers, simply because it's a faint red dwarf, roughly 1,000 times dimmer than our Sun, tucked in the same general direction as its far brighter, far more obvious neighbors. If our literal nearest star could go unnoticed until the early 20th century, purely because it wasn't bright enough to draw attention on its own, it raises an obvious and uncomfortable question. How many other dim, easily overlooked stars are sitting within a similarly close range, still waiting for someone to specifically look for them, rather than simply notice them by accident? The honest answer, based on ongoing survey work, is probably several. Astronomers studying the overall statistical distribution of stars in our galaxy, comparing how many bright, easily observed stars we've catalogued against the predicted ratio of dim red dwarfs that should exist alongside them, have concluded that our current census of very nearby stars is very likely still incomplete, particularly for the faintest, coolest examples sitting at the extreme low end of stellar brightness. In other words, this isn't a solved problem sitting comfortably in the past, resolved by better instruments decades ago. It's an ongoing active limitation in how we currently understand our own most immediate surroundings. Let's talk about why this matters beyond simple cosmic trivia. Because there's a genuinely practical, slightly unsettling angle buried in all of this. Every previously undiscovered nearby object we've found, whether it's a cold brown dwarf like Y0855 or a faint red dwarf that had simply escaped notice for centuries, represents a gravitational presence that has been sitting quietly in our galactic neighborhood the entire time, completely unaccounted for in our understanding of the region immediately surrounding our solar system. We've discussed, in earlier explorations of this topic, how a single ancient stellar flyby, discovered only by reconstructing its trajectory decades after the fact, may have brushed against the outer edge of our solar system roughly 70,000 years ago, entirely unnoticed at the time. That discovery alone should tell you something important. Our awareness of what's actually moving through our local cosmic neighborhood has consistently lagged behind reality, sometimes by tens of thousands of years. If we're still finding entirely new star systems within a few dozen light years of Earth as recently as the past decade, and we are, it's worth asking, honestly, what our current, presumably complete map of nearby space might still be missing. Not in some distant, unknowable way, in a concrete, actively researched way, where astronomers themselves openly acknowledge the census remains a work in progress. So how close could an as-yet undiscovered object realistically be? This is where scientific honesty matters most, because it would be easy to lean into unwarranted alarm here, and that wouldn't reflect the actual state of the research. Current, ongoing infrared and optical survey work, including deeper follow-up missions building on WISE's original data alongside newer instruments, specifically designed to hunt for exactly these kinds of faint, cold, easily overlooked objects, has significantly narrowed the realistic range for any undiscovered stellar or substellar object within our immediate neighborhood. Most astronomers now consider it unlikely that a full, genuine star remains completely undiscovered within just a handful of light years of Earth, given how thoroughly that specific range has already been surveyed using increasingly sensitive infrared techniques. But unlikely is not the same as impossible, and the outer boundary of what counts as genuinely well-mapped space keeps shifting further out as our instruments improve, which tells you something important on its own. If our current surveys were already comprehensive, they wouldn't keep finding new things. They do, regularly. Which means the honest, current scientific position is that our census of the nearest few dozen light years around us remains meaningfully incomplete, particularly at the faint, cold, low-mass end of what's out there, even while the very nearest, most immediate range has become increasingly well understood. Let's widen this out into the bigger, more uncomfortable picture, because there's a pattern worth naming clearly. Humanity has photographed galaxies so distant their light left them over 13 billion years ago. We've mapped structures spanning hundreds of millions of light years across the cosmic web. We've detected the gravitational ripple of two black holes merging over 1 billion light years away. And yet, in our own genuinely immediate cosmic backyard, the stars and substellar objects closest to our own sun, the ones theoretically easiest to study simply by virtue of proximity, we are still actively discovering things that have been sitting there the entire time modern astronomy has existed. That's not really a contradiction, once you understand why. Distant galaxies, however far away, tend to be enormous and blazingly bright, radiating with the combined light of billions of stars, genuinely easy to spot once you're pointed in the right direction, precisely because scale and brightness compensate for distance. But a small, cold, dim object sitting relatively nearby doesn't get that advantage. It has to be found the hard way through painstaking, systematic surveys, specifically designed to catch exactly the kind of faint signal that a spectacular, distant galaxy simply doesn't need in order to be noticed. In other words, the universe hasn't hidden its most distant, most extreme wonders from us nearly as effectively as it's hidden some of its quietest, closest neighbors. So here's the truth we're left with tonight. Our nearest cosmic neighborhood, the stars, and substellar objects sharing our small corner of the galaxy, remains, even now, an incompletely mapped space. Not because we haven't looked, because looking, in this specific case, requires catching objects that are cold, dim, and fundamentally reluctant to be seen. Using detection methods that have only existed in their current, sufficiently sensitive form for the past couple of decades, we found our literal nearest star roughly a century ago, embarrassingly late by any reasonable standard. We found our third nearest star system barely a decade ago, hiding in plain sight the entire time, simply because it was too cold to draw attention to itself. And current research strongly suggests there's more still out there, sitting within a range close enough to matter, waiting on the right survey, the right instrument, the right astronomer to finally notice it. It's a genuinely humbling thought, buried underneath all the astonishing images of distant galaxies and ancient cosmic light. We've learned to see across almost the entire observable universe, and we're still, quietly and methodically, working out exactly who and what is sitting in the dark right next door.